Again, my name is Tyler Evans from BTC Inc., and we've got an amazing panel today. Some incredible thinkers and people who are responsible for a lot of the growth and proliferation of consensus algorithms we've seen. So let me turn it over to our panelists to introduce themselves and their projects and what they've been working on.
Hi, I'm Jae Kwon, and I'm here to represent Tendermint and Cosmos. Cosmos is a network of blockchains. It's blockchains that are powered by Tendermint consensus, a BFT consensus algorithm whose function is to connect to many other blockchains and provide interoperability and scalability. The way it uses Tendermint, it implements a layer of incentivization and disincentivization on top. So it's a proof-of-stake solution built on top of Tendermint.
And Jay, you mentioned BFT consensus. Could you explain what that is for our audience and why that's important for blockchains?
Sure. So Byzantine means arbitrary behavior, and so it's in the context of there's a lot of actors. It could be people in a room, or it could be computers. Usually in the context of computers, and the idea is how do you get all of these entities or nodes or machines to come to agreement about any single thing, and it can be about a single bit or about the last block, and you need to be able to come to consensus despite one or many of these nodes behaving arbitrarily and lying and trying to disrupt the system. So the collection of these malicious actors that are not running the protocol that they should be running, they're called Byzantine actors. It's called Byzantine fault tolerance because we're talking about a consensus algorithm that can tolerate and handle, or in other words, be able to function despite many Byzantine actors. So you might hear things like, oh, this consensus algorithm can handle up to a third of Byzantine actors or Byzantine voting power.
Thanks. Mahnush?
Hey, I'm Mahnush, and I'm representing Definity. And we are building the whole protocol stack to present and function as an internet computer, meaning that the user can compile its program that he's written to any language, and then run it on top of the Definity consensus layer. And so we are using BLS signature aggregation methods to make sure that we can have truly random selection of the producers of the blocks. And also we are using a new method for consensus to make sure that we have fast finality. So we get efficiency and we get security because of these two properties.
Great. And Larry, tell us a little bit about Genaro Network.
Hello, everyone here. I'm Larry, the founder of Genaro Network. So Genaro Network is a programmable public chain together combined with a decentralized storage network to provide developers a one-stop solution. And we creatively use the SPOR, Sentinel Proof of Retrievability, hybrid with POS, Proof of Stake, to make a sustainable consensus mechanism. And it's my pleasure to share my experience with you and meet you all here. Thank you.
And Larry, you mentioned proof of stake. Obviously, the consensus algorithm most people are familiar with is proof of work, like we have in Bitcoin and Ethereum. But I was hoping our panelists could give a little bit of an overview of some of the different consensus approaches and kind of how those play out in terms of the different security considerations.
Sure. So the way I have learned this through reading some papers years ago is that there's of course proof of work, which is a different beast than non-proof of work classical, I call them classical Byzantine fault-tolerant algorithms. And within classical BFT algorithms, which have been developed since the 70s, maybe before, I'm not sure, yeah, there are two families. So one is based on this thing called a common coin, which is randomness, And there's another family of algorithms that don't require randomness and is more deterministic. In the case of Tendermint, it's the latter. So it doesn't depend on randomness, but it's deterministic. So like we have like proposer selection, but it's a deterministic round-robin selection system for now. I mean, we can plug in something else later. Yeah, well, the benefit of that is that it's simple and simple to understand. Conceptually, it's relatively much simpler than other algorithms out there. It's kind of why, because that's one of the design constraints. I think like layer 0 of all this stuff, there's layer 1, 2, 3, but like layer 0 is what are you trying to solve? And in the case of Tendermint, we wanted something very simple, and we also wanted something fast. So like there are these limitations that have been proven for a while about how fast and how tolerant consensus algorithms can be in the context of certain environments. And Tendermint and Definity's algorithm, we approach these limits. So that's one factor, and I guess the other factor is due to the simplicity and the lack of need for randomness. One benefit is it doesn't require it doesn't require like cryptographic algorithms that some might say are not proven yet or are not quantum resistant, for example.
So I like to start with the definition of consensus first. So people know what we are talking about. So in consensus, it means that we have multiple people who are trying to reach an agreement. So each party has an input, and they are trying to reach agreement on the output, and the output should be unique to everybody. So if they reach agreement, they should all have the same output. So as Jay said, there are two ways to do that. One of them is deterministic, meaning that all the parties take turn to propose a value, and then if he's a good party, then people can reach agreement on the proposed value. But another way to reach agreement is that instead of going round robin, that each person propose a value in an order way, you can choose a random person, a random party, to propose a value. That is what proof of work is doing. So proof of work is a way of choosing a party to propose a value in a random way. And that is how Definity is doing it, is to use BLS signatures. So we create randomness using BLS signatures, and then we choose one party to propose a value. But as Jay said, after you choose a party, it doesn't matter. Then you have to run a protocol to reach agreement. And what does mean to reach agreement is that if the party is good, he proposes the same value to everybody. So everybody has the same value at the end of this process. But if the party is bad, because we are considering Byzantine parties, so they can act arbitrary. So he can propose different values to different parts of the network. And then they have to check if they all have the same value or not. This is how they reach agreement. And in proof of a stake, you choose a party based on the stake it has, but you are creating randomness in other way and choose a party to propose a value based on a stake. In proof of work, you use the proof of work to create the randomness. That's a difference. Okay.
Thanks, Taylor, for the question. So I'll first start from my understanding of the consensus and share how Genaro is doing that. In any distributed system, that to design a consensus need to follow the CAP theory. That is that the consistency, the availability, and the partition tolerance. You can't optimize all those three at the same time. So basically, when you design a consensus, you need to figure out that for your user case, that which ones you want to focus more and which ones you want to sacrifice a little bit. And so there are basically two main families of the consensus, and the BFT and the Nakamoto consensus, and focus on consistency and availability each more a bit. So, but in a long run, I like to propose another idea called to think about the sustainability more instead of the user case only. So let's say proof of work, that is a very great idea, but the electricity cost in POW is just too much. So according to research, and the electricity cost in mining Bitcoin only exceeds 169 countries in the world last year. that's a lot. And what is worse, that is a computation towards the kind of useless thing. It's solving the math puzzles instead of doing the useful things like the machine learning algorithm or gene engineering, let's just name it. So, and Genaro thinks we need to find a type of useful computation to kind of replace the proof of work. And also we combine the proof of stake to increase efficiency. So Genaro uses SPR to reprove proof of work. So what is SPR? That is proof of retrievability. So first we create another level, a decentralized storage network. And proof of retrievability means that to prove you that you can retrieve your file anytime you want without actually downloading the file itself. So it's a type of useful computation and has been used for cloud storage for years. So to my understanding that proof of X can be used in a hybrid way to try to increase the efficiency in a secure way. Thanks.
Let's zoom out for a minute here. Why is the choice of a consensus algorithm so important for a blockchain project? Or why is this an ongoing area of research?
Okay, so to follow what you just mentioned, Tendermint was started because someone on the interwebs had mentioned at one point, 2013 or a long time ago, like, Bitcoin's great, but it's got several issues. One of them is that when the price of Bitcoin goes up, the energy required to secure it goes up, and also with many proof of work chains, because miners are so anonymous. Like you can be mining on one chain and switch over to another chain, depending on the compatibility or and so it's hard to have these independent chains, these many proof of work chains, be all secure independently, because essentially like you're dividing the potential security across all these chains, and so each chain is weaker, and you can attack them using economic methods. So that's I think primary, maybe why proof of stake is becoming a lot more interesting today. But the other thing is, scaling has been a huge issue, a topic recently, for years actually, and it's certainly an issue. And the nicest way, I think, of scaling the blockchain ecosystem is by having many parallel chains. Like this is how Silicon Valley does it. This is how we've been doing it for a long time, because conceptually it's like the simplest thing to do. You have these atomic units called computers, and you arrange them and in a certain way, and you delegate tasks, and you have this one be the hub or the router, and then you divide the tasks up, and then you have each one. So like so having many parallel blockchains is the right way to do it, but then the question is, how do you get these blockchains to coordinate with each other? And so the way Cosmos does it, you have two blockchains powered by Tendermint, and they each can be aware of the consensus state of the other. Like one chain can know and be absolutely positive that the other chain had committed some block just 5 seconds ago, and if there's some kind of attack, or if this is not, if anything is wrong here, then there's like a huge economic penalty. So like that you can have assurance that it's going to work most of the time, and if it fails, that the ones who are responsible for it are going to get punished by being slashed or ejected from the system. Now, in order to have this link, and to have a link like this at all is to say that one blockchain needs to trust what like if you want to move coins from one chain to the other, like you have to be really damn sure that that's the right thing to do, and it's exactly the same problem as the Byzantine consensus, the Byzantine generals problem. So by having a fast consensus algorithm with short proofs, we can finally have scalable blockchains by allowing blockchains to communicate with each other, and that's the approach that we take.
And Jay, could you give us some real-world examples of the new types of use cases or the new types of transactions or commerce that's possible because of this parallel blockchain setup?
Okay, sure. So just as an example, imagine if you could take Bitcoins and transfer them through bilateral pegs to the Ethereum blockchain, and if you could actually have a smart contract that manages your Bitcoins. So they're not exactly your Bitcoins because they went through several hops of indirection, and if any of those links fail, then of course you might lose your Bitcoins. But it's still the right way to do it when you're considering all these independent blockchains. So that's one example, scaling obviously. But by having, what Cosmos does is I don't want to hog the mic. What it does is we create we like creating good protocols. So what we call IBC, inter-blockchain communication, is kind of like TCP/IP, and it can be used for all kinds of blockchain-to-blockchain communication purposes. So it doesn't have to be about coins moving. It can also be about information like, well, we want to lock this asset. We want to set this name, set this key value. All kinds of things are possible.
Cool. And Mahnush, tell us a little bit about the consensus that Definity uses and kind of what parameters it optimizes for in terms of speed and security and scalability.
So the Definity consensus first optimized the efficiency and finality. So we reach finality within seconds, within 2 seconds. And this is very important for consensus protocols because if you want to consider Bitcoin reached a final state, and it's not completely final, it's the probabilistic final state after around 1 hour. And it's kind of late for most of the applications because assume you want to go to buy something and use Bitcoin, you cannot wait 1 hour in the store to make sure that your payment is done and you get the service. But within a second is a very important feature of the Definity. Another more important feature of the Definity is that it's a provable consensus protocol. There are 2 ways that we call it provable. One of them is that it's actually, we prove it by mathematics, that it is secure and it has all the properties that it should have. And the other thing is that it's provable, meaning that if one person that is completely outside of the Definity network look at the network, it can see that the parties reach consensus, and they can produce a proof for the party that to prove that it reached consensus on some value or on some block. If you want to do this proof for Bitcoin, you have to download the whole chain, or for Ethereum, you have to download the whole chain, because otherwise you cannot make sure that, okay, this is the final state without knowing what was before the actual state of now. But since we are signing our blocks, you don't need to download the whole chain. You only need to download a few key chains, that is who is the signer, and then you only download the current block, which has the signatures of everybody in the network or a group in the network that can provide a proof. And why it is important, as Jae said, for reaching scalability, it is very important to have sharding or to have multiple chains in parallel. And if you want to have multiple chains in parallel for Bitcoin chain, it's much more difficult to prove what is the final state of the chain. But for Definity, it is a very short proof, and it makes the sharding very easy, and it has better scalability.
And I'll ask you the same question I did to Jae. What are the types of new use cases or applications that this consensus mechanism enables that maybe you're unable to do on today's blockchain networks?
So I think a very important use case that was what Ethereum was trying to do, but it's still a proof of concept for Ethereum. So assume any computation. You cannot wait for 1 hour to make sure that your computation is done. So it's very important to have efficiency when you are doing computation. Maybe for monetary transactions, you can wait, but for computation, it's impossible to wait because you have to do a lot of computation one at a time, and if you want to wait 1 hour for each one, it's not possible. And other things that is very interesting to see, I think, is privacy-preserving computation. So assume that I have some data I don't want to share with the whole world. So currently in blockchain, if you use Bitcoin or Ethereum or most of the other blockchains out there, everybody see what was your data and what was your computation. So the whole data is out there in plain text. But I see if you have sharding, then you can have your shard or your chain that is completely private, and it has only propagate the information as needed. You don't need to put whole information for the consistency out there for everybody to see.
And Larry, I'll ask you the same thing. How about the kind of trade-offs and optimizations that Genaro makes?
To make a short summary, Genaro network satisfies the decentralization a little bit by increasing the efficiency that to elaborate that how Genaro network makes consensus. So as we make a two-layer of the network, the way it works is like all nodes do the proof of stake, and they have some rights to share the storage and become a storage node. And for the top 101 nodes that rank in the system, and they generate block, and this idea is similar to the master node of the DPoS used by EOS, but the difference is that we select the 101 nodes based on their contributions of the storage network to see how much the storage they shared and how long has been used and how much percentage of the storage has been used. And the philosophy is whoever makes more contribution to the entire system and who had the ability to guide the chain. So, and because it's all node consensus, it's only 101 nodes to reach a consensus. So of course it sacrificed decentralization a little bit, but we introduced the second layer of the storage can still maintain the security and increase the efficiency in this way.
I want to talk for a minute about the nothing at stake problem for proof of stake blockchains, and if someone could describe this problem and how you guys are tackling it in your individual projects.
I can start because first we do have this problem. We use proof of stake. So nothing stake is like if someone fork the chain, and if you're a miner and you can support each chains without you have nothing to lose. So you have to have some punishment in the proof of stake chain. But Genaro way is because we introduce another layer on the storage. So only when the nodes have sentinels that comes from the contribution of the storage network can do the verification. So the sentinel is something at stake. So to solve the problem primitively, that's how we do that.
So for Definity, because we are also based on the traditional BFD-based protocols, so at the end of the consensus, we reach finality. So there is only one block that everybody agree on. So even if the adversary produce or introduce a lot of chains to the network, after some time, all the chains are collapsed and only one of them survive. And it doesn't really, we don't have this nothing at stake problem.
So I'd say that you need two things to solve the nothing at stake problem. And one is, you need a Byzantine fault-tolerant consensus algorithm, but not only does it need to be BFT, it also needs to be accountable, meaning that, so what accountability in this context means is that when the blockchain forks, and there's a double spend attack or something, you're guaranteed to be able to figure out who you need to punish to prevent this from happening again, right? And not all consensus algorithms have that. So Tendermint has it because, I don't know if it's simplicity maybe, but so you need to have accountability, and the other part you need is bonding. So you need to have a system where in order to participate in voting, you have to get something locked up, your staking tokens, for example, and in order to get your tokens back, you have to wait a period of time called like the unbonding period. And in the case of Cosmos, it's going to be 3 weeks. And that time allows for the guarantee that if someone were to get duped by some malicious action, some fake commit on the blockchain, then it's okay. You have some time to be able to react to it. You can show the network, hey, look, here's proof that something bad happened. Let's reorganize after pruning the bad actors. So So that way you can mitigate the short range, nothing at stake problem. The long range is another aspect, and non-proof of work chains can't really address it. So the way we deal with that is by circumventing it and say, well, we can't solve it, but what we can do is make sure that everyone understands that they need to sync with the blockchain. Like if you're a full node, you need to occasionally sync with the blockchain in order to know what the latest validator set was. But for light clients, there are much better solutions than that.
Well, this is all pretty weighty stuff. I would ask you guys, if you were talking to someone who's a junior developer or who's new to this subject, where would you point them to learn about these topics and to be able to kind of follow the technical progress in this area?
For us, if you're a programmer, I would say look at the Tendermint code base. It's Apache 2.0, open source, written in Golang, fantastic stuff. If you want to develop, I'd say look at the Cosmos SDK, but it's a different story. If you're a researcher, then look at, there's a new paper that was published with Jarko, Ethan, and myself. Mostly Jarko wrote it in this case, but it's a formal proof of Tendermint, so thank God for that. And but if you're just like, a programmer or you're interested in this stuff, then check out Ethan Buckman's thesis paper, which I think does a great job of explaining the intuition behind everything.
So I think the best way to start is by reading papers. Even programmers, I think for basic intuition of, if you are trying to implement consensus, you have to know the basic intuitions behind it. And I think starting with 20, 30 years old papers is the best way, because they describe things more simpler, because they were the first ones. So the new protocols are more complex. So start with some simple protocols. Maybe PBFD is a nice start. And I think Leslie Lamport has a lot of nice book and papers on the topic, so you can start to read from there. And then they
simpler than PBFT. FYI.
You can try to learn from Tendermint, and the white papers that are on the consensus and are out there are we in the Definity white paper, we try to describe all this concept very easily, and we try to have a proof that is readable by even people who are not like researchers. And looking at the code base is also very helpful. So choose the project that you like. I suggest Definity. And look at the code base that we have, and then you can get yourself more familiar with the topic.
I think the easiest way is to start from Ethereum, because it's most straightforward one, I think. So I think if you are interested in the decentralized storage network used in the blockchain projects, and I encourage you to just Google the proof of retrievability. There are many papers, and some are published recent years, and you can find the Sentinel ones that our code just implement that paper. That's very useful. And as for the consensus, so we're going to launch our technical yellow paper very soon. So I encourage you to follow us, and maybe next week, and you can see our yellow paper to talk about how we combine the SPUR together with the POS to solve the nothing at stake and long-range attack issues, etc. That's all.
Well, we're out of time, but I want to end on one last question. What are you guys most excited about in this space, or what developments?
Can't wait to launch.
So I'm excited about the fact that now we can have millions of people to agree on something. When I started to work on consensus protocols, it was only possible between 10 parties, the provable way, the PBFD way. Now it moves to 100, it moves to 200, and now we are talking about millions of people agreeing on something at the same time, which is very interesting.
Why I'm excited about the blockchain. So I think the first time I come to the blockchain industry, I think it's a decentralized distributed ledger. But then I noticed that blockchain is much more beyond just ledger. It's actually an option to the cloud that can provide developers more ways to implement the decentralized applications and to protect the data's privacy and have the similar functions of the cloud. So I think that's why I'm excited about this. And of course, consensus is the core part to implement all these things.
Well, thank you guys very much. Please join me in giving them a round of applause.